Okay, we are going to continue our discussion on phase diagram of mixture. We are talking about mixture. We have been talking about liquid mixture A plus B. And in the previous lecture, we've been talking about the phase diagram where you have pressure as the y-axis and the composition as the x-axis, right? And this phase diagram was indeed obtained at constant temperature or any specific temperature. And from this phase diagram, the information that we were able to collect was basically if the composition and the pressure is given at that temperature. So if we reach if we are in this point, the phase diagram basically tells you how many phases there would be in the equilibrium condition. P could be one, forming single phase, well mixed. I'm sorry, we've been right. You can have well mixed single phase with P1. You can have single phase. You can have gas mixture forming a single phase as well. And you can have an equilibrium between liquid and the vapor phase. In that case, you can have P being equal to 2. Now we are going to talk about a phase diagram, this time where we're going to have pressure being constant, and we're going to see how we're going to see the temperature versus composition relation. We're going to see a phase diagram or a map that gives you information of what's the phase that gives you the minimum Gibbs energy possible. And that's going to change with temperature and composition, right? And this information is going to be obtained or collected at constant pressure condition. So if we look into this map, we know the composition and we know the temperature, we should be able to find how our mixture exists. It may exist in a single phase, it may exist in 2 phases, and those are the information that we want to collect. So let's, okay. So A plus B mixture, and let's talk about liquid mixture. And let's say the boiling point of TB or pure B is higher than the boiling point of pure A. So what I mean by this is that the vapor pressure of pure A at the given condition is going to be larger than the vapor pressure of pure B. And let's say I have this diagram here where I have a temperature and z-axis, and z of course means the composition of the mixture. I'm going to use x to describe the liquid composition, and I'm going to describe y. I'm going to use y to describe the vapor composition, right? And if ZA is equal to 0, I mean that I have pure B. And if ZA is equal to 1, I mean that I have pure A, right? And let's say at T equal T1. So let's say this is T equal to T1. Let's say I have a liquid mixture. And let's say they are well mixed. I have a phase 1 liquid mixture. And in this case, let's say I have no vapor that is in equilibrium with. So this is pure liquid. This is a liquid mixture, no vapor phase. And the composition of this liquid, let's say, is equal to A1. So that's going to be A1, for example. And here's what I have. And let's say I increase the temperature. So in this phase diagram, I'm going to increase the temperature. And as you increase the temperature, and you're going to reach one point where you're going to start observing a vapor phase, because either A or B is going to evaporate, right? So let's say this is a point. You, for the first time, observe existence of this vapor phase, right? So in this point, at T being equal to T equal 2, you're going to have, well, liquid will start to boil. And if they boil, there should be an equilibrium between liquid phase and vapor phase, right? You have this equilibrium between these two phases. And what would be the composition of liquid at the moment of vaporization, and what would be the composition of the vapor at the moment of boiling at this specific point? Well, I guess the composition of liquid is going to be equal to A1, because it's really the same liquid I have, right? So here, let's say I have started from A plus B mixture. They were all liquid, they were all mixed, but at this point, I'm starting to observe a vapor phase or boiling, something going on. A plus B, liquid. Now I have, I don't know what this is, but I have a vapor phase here. Something's boiling. And the composition here is going to be A1. And what about the composition here? Let's say the composition here is A1 prime. And because it's a vapor phase, I'm going to use YA. And the composition here would be YA should be A1 prime. And my question here is that what would be a larger value? Would A1 be larger than A1 prime, or A1 prime be larger than A1? The answer, you can make the answer based on this information here, or the vapor pressure here. And it tells you that the vapor pressure of A is higher than the vapor pressure of B, right, in the pure state. What I mean by that is, if they start to boil, more A is likely to be evaporated compared to B, right? Because you have higher vapor pressure, because the boiling point is lower. And therefore, if the composition of the liquid here was, let's say this is 0.2 or 20%, and you start observing something boil, that vapor is going to contain more A than in the liquid phase, right? Because the vapor pressure is higher, right? So A1 prime is going to be a larger value than A1. And let me put, and at that temperature, let's put this to be A1, right? And if you do a similar experiment from different composition to start with, let's say you start with A2, right? And then you're going to observe liquid starting to boil at different temperature, T2 prime. And at that point, you're going to observe a vapor phase with different composition that may be A2 prime, and such and such. So if you connect all these points, and you can draw a line that looks like something like this. And if you collect all these lines obtained from the vapor phase, you should be able to obtain a line like that. And this line, the red line, of course, tells you the vapor composition. Well, it tells you about the vapor. And here, well, let me do this in black. This is about liquid, right? And what do we learn from this phase diagram here? So let's go back to the beginning again. At T equal T1, we had liquid mixture, and they A and B mixed well. So we had A plus B, and here we had P being equal to 1. Only single phase existed. If you increase the temperature up to here, for example, the mixture is going to be pure vapor phase, and it's going to be well mixed vapor of A and B. So above here, you're also going to have P being equal to 1. But in between these two lines, you're going to have the P is going to be equal to 2. And that's because you have both liquid and vapor at the same time. They coexist, and they have different composition. Liquid has different composition to a vapor at this temperature range here, right? So here is something that you can do. Let's say I start from here, P being equal to 1. I had this liquid mixture, A plus B, and I increase the temperature up to here. And what I'm going to observe is I'm going to observe for the first time the existence of the vapor phase. That vapor phase is going to have a composition of A1 prime, and the liquid that has not been evaporated yet is going to have a composition of A1. What's going to be the amount? Like, what's going to be the ratio between the liquid phase and the vapor phase at this point? You're going to have to use the lever rule again, as you've learned in the previous lecture. And if you think about the lever rule here, if I magnify this, I have black point here, red line going this and here. And it tells you that really, if I'm right here, the ratio, well, I can't define the ratio because it's actually 0, and it's a constant value here, right? And it, according to the lever rule, it tells you at this specific point you have a 0 amount of vapor, or you can say that the vapor phase it has just started or has appeared at this point, and 100% of the mixture are in the liquid phase. What would happen if you further increase the temperature? You now has increased the temperature up to here. Then the temperature, the overall composition is going to be still 0.2 here. And in this case, you have two phases. One is the liquid phase, the other is the vapor phase. You're going to have a liquid phase following this composition. You're going to have a vapor phase following this composition. Why is the liquid phase composition at T equal T3 lower than the composition at T being equal to T2? That's because more A has been evaporated and became gas phases, vapor phase, right? Therefore, in the liquid mixture, you would have less A than you had at lower temperature, right? So now the composition of liquid phase is lowered. And if you think about the vapor phase, the vapor phase would follow the composition right here. This composition is lower than the composition here at T being equal to T2. And this because as the temperature is increased, there is going to be more contribution of B compared to what it was down there, right? So this is how you make the interpretation. One more thing that I can think about is, let's say I started from here again, and I elevate the temperature, and let's say I have somehow, let's say I was able to collect the vapor phase. So what I'm going to do is, I had this A plus B liquid mixture, and then I'm going to increase the temperature. It was liquid originally, and I elevated the temperature. It's still liquid, but I also have the vapor phase as well. And this liquid has a composition of A1. This has a composition of A2. And let's say I was able to somehow collect this vapor separately. So I'm collecting this vapor separately. And let's say I have cooled this down, only this part, and lowered its temperature. So I'm going to collect this, and I'm going to lower lower the temperature. And when I reach the temperature below here, everything I collected from here would become a liquid phase, right? Because now I'm in this pure liquid zone of the phase diagram. I have reached here. And this liquid is going to have a composition of A1 prime. So A is going to be A1 prime. What did I do here? So I originally had a liquid mixture that has a composition of A1. I boiled it, and then I collected the vapor phase, and I cooled that down. And what I had as a result is a liquid that has more composition of A than it was before I did all this experiment. So I originally had a liquid with composition A1. Then now after doing all this, I have this liquid. Let's say I lowered down the temperature back to original T1. The composition is now A1 prime. So now I have more, because A1 prime is larger than A1. What I mean here is that if I collect the liquid mixture, that's A plus B liquid, but now I have more A here than it was there, right? This process is one way to obtain this process is one way to increase the composition of A. Let's say if I continue this process over and over, what I mean by that is, let's say I have started with liquid composition A1. I started with composition A1, I boiled it, I collected the vapor phase, cooled it down, and then I boil this again. And here I'm going to collect, and at this point, I'm going to observe the vapor phase for the first time. Let's say I have cooled this, collect this separately, cool this down. It's going to have a composition here. I'm going to boil this, collect the vapor phase, and cool that down. And by doing this over and over, I should be able to obtain pure A, right? I started from A plus B mixture, but I can reach a composition with high purity of A, or higher purity of A, or higher composition of A, right? This process is known as a distillation. It's one of the most important topic in chemical engineering, and there are two types of distillation. One is simple distillation, which is simple, of course, this is in simple, typically, let's say you have a volatile liquid and non-volatile solute. And let's say I want to separate these from each other. A good example is, let's say I have a water added with salt. And let's say I want to collect H2O. How would you do this? I guess people would know that you boil it, right? You boil the mixture and you collect the vapor and cool that down, and you're going to obtain pure water, right? That's basically how you can obtain water from pure from seawater, right? So that's a simple process, and it's simple because the solute cannot really become the vapor phase. It's a non-volatile. But things get a little bit complicated when you have both volatile liquid and volatile solute, and that's called fractional distillation. And here you have volatile liquid as well as volatile solute. And so this should have a vapor pressure. This should also have a comparable vapor pressure. And the example that we had here is a good example where fractional distillation is needed. So what you're going to do is basically you're going to repeat cycles of boiling. So you're going to increase the temperature, right? And you're going to separate the liquid phase and the vapor phase, right? And you're going to condense the vapor phase. You're going to condense the vapor phase, right? So you're going to lower the temperature, and then you're going to boil it. You're going to separate the liquid and vapor phase again. And then if you run the cycle, you're going to collect the composition of the liquid that you collect is going to reach towards this end, or maybe this end, composition being equal to 1 or composition being equal to 0, right? And you're going to learn about this more perhaps in the thermodynamics class or separation courses in your junior senior year. But let me introduce this important concept of theoretical plates. Theoretical plates. In fractional distillation. So let's think about a case, or let's go back to the case we had: temperature, composition, plot, and let's say we had a phase diagram that looks like this, and let's say I started from here. What I'm going to do is I'm going to increase the temperature. Then I'm going to have both liquid and vapor in equilibrium. I'm going to cool this down, right? I'm going to collect the vapor. I'm going to cool this down, and I'm going to boil this again. And then I'm going to have liquid and vapor composition in vapor in equilibrium. I'm going to collect the vapor, cool that down, and I'm going to boil it again. Liquid, vapor in equilibrium. I'm going to collect the vapor here. And if I do this 1 time, 2 times, 3 times, I reach, let's say I have reached ZA or XA being equal to 99%. Another example where I have temperature and ZA that looks something like this. And I start from this composition again. And let's say I do the same thing. I boil this. I'm going to have both liquid and a vapor in equilibrium. I cool this down. I have liquid and vapor again. I separate the vapor phase, cool this down, boil it, separate the vapor phase, cool it down, and let's say I do this 5 times and reach this composition where I have XA being equal to 99%. The theoretical plates basically explains the number of cycles that is needed to obtain desired composition. Let's say in this case, let's say I wanted to obtain 99% of A in the mixture, and I start from here. The theoretical plates for my mixture following this phase diagram is equal to 3. I need 3 cycles of repeating boiling, separation, condensation. Whereas here, I needed 5 cycles of boiling, separation, and condensation and such, right? If you have a larger difference in the boiling point, this point is actually the boiling point of, what is it? It's a boiling point of pure B, right? Right, because if you think about it, that's where you have ZA being equal to 1. It means it's pure B. And this point is where B becomes, it's the temperature where liquid B becomes a gas phase B, right? Liquid would become gas phase. So this is really the boiling point. Here's the boiling point of A. So if TA star and TB star are different by a lot, then the theoretical plates you estimate based on the phase diagram is likely to be a smaller number. If the boiling point, the difference in the boiling point between B and A is not so much, if they are very close, you need more cycles of fractional distillation to obtain pure A or pure B, right? I think that makes good sense. Let's say one of the substance has a boiling point of 102 degrees Celsius, and that's mixed with water, which has a boiling point of 100. It's really difficult for you to separate your substance with water based on distillation because the boiling point is very, very similar, right? Whereas in the case where you have your substance that has a boiling point of 500 degrees Celsius, for example, and that's mixed with water. And it's really easy for you to separate your substance or water from the mixture by boiling up, collecting the vapor phase, and repeating the cycles again and again, right? So depending on your information here, the vapor pressure of the pure phase, and also depending on how your phase diagram looks like, the theoretical plates is determined, and based on the theoretical plates of your mixture, you should design your chemical engineering process, right? Overall, you should design all the plants, and you should design how many cycles of distillation it should follow, right? So that's going to be a very important topic later, well, in your maybe next year, next year. And that was theoretical plate, right? So we've been talking about, this is a relatively simple phase diagram, but there are some phase diagram that looks like this. So it's a temperature versus composition plot. But and this point is the boiling point of B. This point is boiling point of A. But now I have a plot that looks like this, which looks crazier than before, right? It was like this. So it looked like before it was relatively simple when we had a phase diagram that looks like this, right? I mean, this is complicated, but this is simpler. Now this something looks more complicated here. And what's the message that we can learn from this phase diagram? Same as here. Here I'm going to have pure liquid phase. I'm going to have pure vapor phase. Here I'm going to have liquid and vapor phase in equilibrium, right? Likewise, here I'm going to have pure liquid phase only, and this liquid phase is going to be mixture of A plus B. Here I'm going to have single phase. It's going to be vapor mixture of A plus B. Here, P is going to be, well, here and here, P is going to be equal to 2, and I'm going to have a liquid phase and the vapor phase. The liquid phase would follow the composition XA drawn in black line. The vapor phase is going to follow the composition drawn in the red curve here. And what's really interesting about this mixture is that this point, so this, if I start from this composition here, let's say this composition is B. If I start from here and I try, so I have this mixture of A plus B liquid, and I'm trying, let's say I try to boil my mixture. Usually, you would expect that the boiling point of my mixture is going to is between the boiling point of A and B. Well, let me write an example here. Let's say the boiling point of A is 70 degrees Celsius. Boiling point of B is 100 degrees Celsius. And let's say you have a mixture of A plus B. What would be the boiling point of this mixture? When would you start observing a vapor phase? I guess as a first approximation, you would expect some value lying between 100 and 70, right? And that was the case when we had a phase diagram that looks like this. But here, what this phase diagram tells you that if I have started from this composition, the boiling point is actually higher than TB star, and of course is higher than TA star. So it tells you that the boiling point is maybe 130 degrees Celsius. The boiling point is higher when they are mixed. What does what does it tell you? And why would this happen is something important that you should think about. And it basically tells you that they don't really want to evaporate. They don't really want to be vaporized. They like each other so much, A and B, they like each other so much that they don't really want to get separated into vapor phase, right? They like each other more than themselves, right? If the interaction between A and B are so strong, stronger than the interaction between A and A or B and B, and the temperature that breaks this interaction is basically the boiling point, right? The temperature that breaks this interaction is the boiling point of B. But when you mix them and you want to vaporize them, you have to break this interaction so that this liquid become vapor. And if the interaction in the mixture is even higher than their pure state, the boiling point is going to be higher. So in this case, you can obtain a phase diagram that looks like this. Now then, so let's say you had this phase diagram, and let's say I start from this composition here, and let's say this is A1. I'm going to no, never mind. Let's say I started from similar to what we had before. Really? Okay. Oh, yes, yes. Okay, let's say I start from here. And let's say I do the same thing. I'm going to increase the temperature, right? And then at this point, I'm going to observe a vapor phase that has this composition. If I have collected this vapor, cool this down, let me draw it. More precisely, I started from here, I increased the temperature, then composition of the vapor I have is here. I cool this down and then increase the temperature. And if I repeat the cycle here, I'm going to collect pure A here, right? That's what I'm going to do. But let's say I do a slightly different experiment. I increase the temperature, I observe the vapor, and I'm going to continue increasing the temperature up and up and up. And then I'm going to reach this phase where I'm going to have vapor phase only, right? Here I'm going to have vapor phase only, no liquid mixture, and well, no. Let's put the. Let me explain this part here in a larger scale. So I have a line that goes like that here, and a line that goes like here, and let's say this point is here. So I'm going to increase the temperature, liquid phase in equilibrium with a vapor phase, right? And if I think about the lever rule, I have 0 vapor phase and everything's are in the liquid phase at this point. Let's say I increase the temperature up to here. I have a liquid phase, I have a vapor phase, and the relative amounts between the liquid phase and vapor phase is going to be determined by the lever rule. So I still have more liquid than the vapor phase, right? I increase the temperature up to here. Now I have a liquid phase here, vapor phase here. The relative amount between the liquid phase and the vapor phase is now going to be reversed. Now I have more vapor than the liquid, right? And if I reached up to here, liquid phase, if it exists, would have this composition. The vapor phase would be in this composition, right? And the relative amount between the liquid phase and vapor phase, I have 0 liquid, and I have most of them are the vapor phase. So if I do this, I'm going to have a liquid phase and a vapor phase. And I'm confused at some point here. And right. And let's say I have collected this small amount of liquid here, and cooled it down. So I have a liquid that has lower composition than it was A1, and I boil this and repeat the same thing again and again. If I do this again and again, what I'm going to follow is a route like this. I'm going to increase the temperature, collect the liquid phase, increase the temperature, collect the liquid phase, increase the temperature, collect the phase, and I'm going to go along this curve and reach here. If I started from this composition here and do a similar thing, I should be able to reach this position as I repeat the cycle again and again. And what would happen if I reach this point? What would happen if I reach this maximum point there? Once I reach this point where I had this the maximum height from this plot, the composition from there, where the red curve and the black curve meets, the composition of the liquid phase, which is drawn in black, and the composition of the vapor phase, which is drawn in red, are going to be the same. And if they are the same, you can't really have different composition between liquid and vapor. And therefore, even if you repeat the cycles of boiling, condensing, boiling, condensing, boiling and condensing and such, you can't proceed. You can't change the position in the phase diagram, and your composition is going to be fixed here. And this type of a condition is known as okay, yeah. So you're going to reach a composition where the composition doesn't change along the vaporization, and this composition is called an azeotrope. And it's really, it's called azeotrope because the boiling point doesn't change, or the boiling doesn't change the composition. Whereas in other case, if you boil it, right, if you boil it in this composition, because the composition of liquid and vapor is different, as it boils, the composition of liquid and vapor is going to continue changing, right? But at this composition, that's not going to happen, and that's what this azeotrope is. This was the case when you had favorable interaction between A and B. But what would happen if the interaction between A and B are not so favorable? So let's say the interaction between themselves are much stronger than interaction with each other. Then in this case, you're going to have a curve that looks like something like, you can have a curve that looks something like this, which is perhaps the opposite shape of that, right? The boiling point of the mixture in this composition is going to be lower than the boiling point of the pure state. Breaking up the interaction between A and B is much easier. You need lower temperature in order for you to boil the AB mixture and make a vapor phase, right? And this composition is also known as the azeotrope, azeotrope composition, right? That's end of one topic, and let's move on to the second topic. Now we're going to talk about liquid mixture. And now this mixture is partially miscible. So above here, in the previous phase diagrams, if we think about the liquid phase here, if we think about the liquid phase here, we never consider that A and B would phase separate, right? They always formed a single phase. P was equal to 1 in the liquid phase. It was same for here, right? We only had a single phase when we talk about the liquid phase. But now let's think about the case where we have a partially miscible A plus B mixture. And let's think about the temperature versus the composition diagram again. If you have, so here's the temperature, here's the composition, and usually it's mixed and liquid, so I'm going to use XA instead of ZA. And let's say I have a specific temperature, T1 or T prime. They are partially miscible. What I mean by this is that if you have more A, much more A than B, so if you have much more A than B, or if the composition is large or close to 1, I'm sorry, if the composition is close to 1, they will be mixed, right? For a partially miscible mixture. If you have more B or much larger quantity of B than A, and XA being close to 0, they will be mixed. But when you have comparable A and B, so if XA lies somewhere close to 0.5, they will not be mixed and they will phase separate. And that's going to be, in this phase diagram, you can write it, you can write it, you can present this information like this. When XA is small, they're going to form a single phase. What I mean by this is that they are going to mix well. When XA is close to 1, they can also form a single phase. They are going to form a well mixed single phase, right? But in the blue one, you have more A. The red one, you had more in the red one, you had more B, right? And in between here, they don't like to be mixed. They would phase separate. So you're going to have two phases in this condition. What would happen if you increase the temperature up to T double prime? As you increase the temperature, usually the entropy effect increases. So the entropy increases, and that causes that favors A and B to be mixed well with each other. And as a consequence, this range of single phase would increase here. So at T double prime temperature, up to this composition, you can have a single phase. And up to this composition, you can have single phase. And only between this composition, you have two phases, or they are immiscible, right? So if you do this over range of temperature, you should be able to draw a line that looks like that looks like this. If you draw the boundary, you're going to have a boundary between single phase and two phases. I'm going to draw this in a pink curve, and there should be another boundary here that separates the phase two regime between immiscible mixture and well-mixed single phase mixture, right? So you should be able to draw a phase diagram that looks like this. And this curve and this curve might meet. They can meet at a single point. And once these lines cross each other, then if the temperature is higher than, let's say this temperature is T triple prime, and if the temperature is higher than T triple prime, then A plus B will be mixed well, no matter, regardless of the composition, right? So here you're going to have P being equal to 1 at any time, right? So if I draw this again, T for a liquid partially miscible mixture. For composition, I can draw a phase diagram that looks like this and that. And this temperature is known as TUC, and that's upper consolute. Well, it's upper consolute temperature, or upper critical temperature. So if you reach temperature above TUC, they will form a well-mixed mixture regardless of the composition. Below here, you can have phase separation, you can have single phase, depending on the composition that you are looking at, right? That's the phase diagram of a liquid-liquid mixture. And the reason you had upper consolute temperature is because as you increase the temperature, the entropic effect is going to be increased, and they favor A and B being mixed with each other. But you can also have a case where you have lower consolute temperature, or lower critical temperature. In that case, you're going to have a phase diagram. So let's say I have lowered the temperature using the same axis. Let's say I have lowered the temperature, and this curve can go back to this shape here, and this curve can go back to this shape here. And it tells you that here you had two phases, single phase, and once you go below this temperature, which is the lower critical temperature or lower consolute temperature, now you have single phase no matter what. And this is somewhat strange. And what does this tell you? It tells you that at lower temperature, they like to be mixed. And as you increase the temperature, they don't like to be mixed. That's something strange. And the origin here is going to be more enthalpic origin. Here we had entropic origin that made immiscible or partially miscible liquid to become fully miscible at higher temperature. A partially miscible liquid here at lower temperature is now going to be fully miscible, and that has more of an enthalpic origin. A good example here is something like water and triethylamine. They at low temperature, they can form a complex structure at low temperature with a small thermal energy provided, smaller vibration, smaller energy to do crazy things. They have this interaction, enthalpic interaction, forming a complex, and that complex makes the water and triethylamine to be mixed well at lower temperature. And as you increase the temperature, this weak interaction is broken, and then A and B, they tend not to be mixed, and they tend to phase separate. So in a special case where you have a good interaction at lower temperature, you can have a phase diagram containing a lower critical temperature, right? Now, let's think about distillation of partially miscible liquids. So I'm talking about A plus B, right? And they are now partially miscible. Before, when we talked about this, or this, right? If we go back to here, that's where we learned the distillation process. We had A plus B mixture. They were miscible, right? We had miscible mixture A plus B, and we were talking about distillation based on equilibrium between the liquid phase and vapor phase. The second topic that we learned was a partially miscible liquid, where you have a phase diagram that looks like this, or maybe a phase diagram that looks like this. Now let's say I want to distillate a mixture forming a phase diagram that looks like this. How do you do this? I'm going to increase the temperature. I'm going to increase the temperature so that I start observing the vapor phase, right? So what I'm going to do is, let's say this is a temperature axis, and at this middle temperature range, I'm going to have liquid, right? And the liquid may form a partial, is going to be a partially miscible liquid. So therefore, I'm going to have a phase diagram that looks like that. Composition, or ZA. I'm not going to look at the lower temperature. Let's say I have a phase diagram that looks like this, right? And this temperature is upper consolute temperature. Above the upper consolute temperature, they are fully miscible. Below the TUC, they are partially miscible. So in this composition, they are going to have two phases. Here, I'm going to have one phase. I'm going to have one phase, right? And I want to distillate them. And in this case, you're going to, so in this case, when you have an upper consolute temperature, it tells you that interaction between A and B are not strong, right? Not so strong. They're not so strong because, and therefore you had these two phases. And when interaction, and in this case, where you have two phases that don't like each other so much, if you think about the vapor versus liquid phase diagram, you should be able to draw a line that looks like this. And this curve is what we've learned from here, for example, right? When the interaction between A plus B is not strong compared to themselves, and that's why we had this partially miscible liquid. That's why we had a partially miscible liquid at lower temperature. A higher temperature, you're going to have a curve that looks like that, right? So in this case, let's say I have a composition here to start with. I'm going to, let's say I start from composition here. I'm going to increase the temperature, right? And boiling starts at here, and I'm going to collect the vapor phase, cool it down. If I cool it down to this temperature, I'm going to have a single phase, right? Well mixed mixture of A plus B. But if I cool it down to here, I'm going to start observing the phase separation. If I further cool it down to this temperature, I'm going to have two phases. Two phases are liquid phase 1 and liquid phase 2. Liquid phase 1 would follow this composition. Liquid phase 2 would follow this composition. So liquid phase 1 following a red curve. Liquid phase 2 would follow this composition. Of course, the amount between liquid 1 phase and liquid 2 phase is going to be depend on the lever. So in this case, I have a larger wing on the left side than the right side. It tells you that I have more L2 than L1, but they are going to be phase separated, right? That's something that you can learn from the phase diagram that looks like this. But this was the case where you had a zone or a range of temperature where pure or single phase of liquid mixture could exist. But sometimes you can have a phase diagram. It looks like you can have a phase diagram that looks like this. Here you have two phases. The two phases are liquid 1 and liquid 2. So they are liquid mixture. And here I have a single phase, and that's liquid 2 phase. I have single phase. This is liquid 1 phase, where I don't really need to have a line here. I need a line here. Here I'm going to have two phases, right? And the two phases is going to be vapor phase and liquid 2 phase here. Here I have liquid 2 phase. Here I have liquid 1 phase. Here I have two phases. That's going to be vapor phase and liquid 1 phase. Here I have one phase, which is the vapor phase. It looks like a crazy phase diagram here, but all it is in fact, let's say I have somehow removed this range of temperature in this phase diagram. Let's say I have removed this away and connected the lower part and the upper part. You're going to have this type of a phase diagram, right? So this is a case when you don't have a range of temperature where you had P being equal to 1. And in this case, now let's say I have started the distillation maybe from here. I boil the temperature, I increase the temperature. I'm going to start observing a vapor phase, right? And let's say I have cooled this down. I cool this down, and I'm going to if the temperature goes below here, I'm going to have a liquid, and this liquid is going to be phase separated into two phases. One phase is going to be P1 or L2. The other phase is going to be L1. And the relative amount between L1 and L2 is going to be determined by the lever rule. Right? And let's say I have continued this, and increase the temperature and temperature, collect the vapor phase, cool it down. If I have repeated cycle, I should be able to end up reaching this azeotrope point, right? And once I reach this here, once I reach this here, even if I increase the temperature, the composition of the vapor and the composition of the liquid is going to be the same. I should not be able to further distillate one component from the other, right? So that's the complicated story today. And we will continue on discussions on the phase diagram in the next class, right?